2, 1. Alright, so we now have the Riemann integral in our possession, and a rigorous definition thereof. So it is now time, once again, to go back and prove all of those things we told you were true about the Riemann integral back in calculus, and of course we're going to do it precisely and rigorously. And let's just get going. So, first things first, constant functions are integrable, and their integral is exactly what you think it should be. Just the constant times the length of the interval. And again, that should make sense because, recall that this is supposed to represent area under a curve, and if you've got a nice flat line, that means we got a nice thick rectangle, so height times width gives me the area. It's all good. Alright. Okay, but that being said, that's not a proof, so let's actually work for the details of this. And the way we're going to attack this is to basically go every partition behaves in the exact same way. Specifically, if you do take a partition, well, alright, then the infimum of f on the kth subinterval will just be alpha because it's constantly equal to alpha. Same thing with the soup. And thus, when we look at the lower and upper Darboux sums, we just get, hey, alpha times b minus a and alpha times b minus a. So it's got to be that the lower and upper Darboux integrals, since the set consists of a single element, alpha b minus a, so the upper and lower Darboux integrals are equal, so we must be Riemann integrable, and the value of the integral is alpha times b minus a. Super, hey, not a bad one to start with. It works. It just works. 16 times the detail. It's good. Alright, beautiful. Okay. Alright, well, constant functions are integrable, and their integrals are what you expect them to be. Alright, now equipped with this, we can now prove one of the very important facts about the Riemann integral. Half of the fact that the Riemann integral, just like integration, is linear. Whereas with differentiation, we did the linearity as 1. For integration, it's going to just be better if we do it separately. So we will prove that if you have a Riemann integrable function, again, on a non-degenerate interval, okay, then scaling it keeps you Riemann integrable. You can't just scale something and then break the integrability of it. And furthermore, the integral of the scaled function is the scaled interval. Okay, the scaled integral, not interval. Okay, so now here, our proof is going to be very different than what the textbook does, because, as we noted in the last video, we went a little bit off script, where we specifically focused on proving that Riemann sums actually characterize the Riemann integral. Lebel leaves that as homework, which I sort of agree with, but at the same time, I'm like, no, you really, those proofs are not particularly easy, so... But anyway, so our proof of this is going to use the Riemann sum characterization, and as you'll see, it gives us an incredibly quick and easy proof. Lebel attacks this using Darboux sums, and it's a little clunky because you got to consider a couple of cases, and depending if alpha is positive or negative, and so it's not too bad, but the Riemann sum version of it goes a lot faster, but we do have to do cases ourselves, unfortunately. And one of them, easily enough, is, well, let's just take alpha. If it is equal to 0, well, then our function is nice and constant. And as we just proved, every constant function is integrable, and the integral is exactly what you want it to be, so things work out. Okay, so let's go ahead now and further assume that our alpha is not equal to 0. Okay. Since our function is integrable, that means given any epsilon, I can find a delta, so that all partitions with mesh size strictly less than delta, the corresponding Riemann sums get within, in this case, epsilon over the absolute value of alpha of the Riemann integral. Okay, cool. Right, so again, we prove that integrability is equivalent to this epsilon delta characterization. Okay, so what am I going to do now? Multiply by alpha. Alright. So for any partition then, with mesh size less than delta, we know that this has to be true. So just multiply this to the other side. Again, it's a non-zero, so we can do it. Distribute. distribute, and oh hey, look, the Riemann sums for the function f times alpha get within epsilon of. That's a weird. what's the parentheses around the f there? That's. I'm on that A1 stuff. You know what I'm saying? All right, get it over there. Side note, that actually is not that notation specifically for function. This notation, it reminded me of this one, so hold on, it'll come back in. So some people write functions like this, where like you're supposed to read it from where x is the input for the function f, rather than reading f of x. And yeah, those people are lunatics. Anyway, it reminded me of that. It looked like that for because the complete opposite of what I had written. Oh, now it's a capital. What the hell's going on? Oh man. Okay. Anyway, all right, cool. All right, good stuff. All right, so there we go. The Riemann sums for the function alpha times f, given any epsilon, any partition with mesh size strictly less than delta. All of those Riemann sums get within epsilon of this, so it follows that the scaled function is Riemann integrable, and the thing that it integrates to is exactly what you want. Beautiful, wonderful, straightforward proof. I love doing this proof with the Riemann sum rather than the Darboux stuff. Not that there's anything wrong with the Darboux stuff, but right, the Riemann integral characterization, right, this has a summation part to it, and this part is very clearly like, I can scale and add it and it behaves correctly. Speaking of adding, let's get the other half of the formula. So now we will prove that given any two Riemann integrable functions, their sum remains Riemann integrable, and the integral of the sum is the sum of the integrals. Beautiful. Okay, so that goes exactly how we learned it in calculus. And again, we're just being a little bit more precise and rigorous about it. Okay, so again, our proof here is going to be very different than the proof Lebel does, because Lebel attacks this directly with upper and lower sums, and it's not bad, but again, if you've got Riemann sums at your disposal like we do, this proof is easy peasy. Give it an epsilon, there is a delta, so that my Riemann sums get within epsilon over 2 of the integral, and that's good for any partition whose mesh size is strictly less than delta. Similarly, we could do the same thing for G. Given any partition whose mesh size is within eta, then the Riemann sums of those corresponding partitions get within epsilon over 2 of the integral of G. And oh hey, look, it's an epsilon over 2 proof. I have some deltas. Take them in, get a partition less than that, both apply, we're done. That's it, right? That's right. We've done this style of proof so many times, and we're just doing it again. With just now our deltas got a little bit more going on, but it's still given an epsilon, there's a delta, so that things work the way I want it to. The same way that limits went, the same way that continuity went, the same way differentiation goes, integration is no different. Given epsilon, there are deltas, so that things work. Alright, so the delta we're interested in is the minimum of the two I've already found. We'll let nu equal that. So now take a partition whose mesh size is strictly less than nu. Then the mesh sizes need to be strictly less than delta and strictly less than eta. So if I pick some elements that live in any of these subintervals here, well, since the mesh size is less than delta, we know that this is going to get within epsilon over 2. And since the mesh size is within eta, we know that this will get within epsilon over 2. And just a classic with epsilon over 2 proof. And there we go. The sum of two functions is Riemann integral, and its integral is exactly what you want it to be. Nice, simple, straightforward. Given an epsilon, we get 2 deltas, take the minimum, and we use that. Wonderful. Right, and that sort of formatting, right, is very common in analysis. Right, Weierstrass really knew what he was. He once he got that epsilon delta thing, he really he cracked that egg, He really cracked that egg, Yeah. Beautiful. All right, nice. All right, so we've now proven that every constant function is integral, and its integral is what you think it should be. Scaling any integrable function gives you what you think it should give you, and it's the same thing for summation. So what else is there to discuss? Well, a natural thing, before we get there, a natural thing, once you've got scaling and you've got adding, is get multiplication, which Lebel actually leaves out, which is weird. So our next goal, our next task, is to prove that the product of two Riemann integrable functions remains integrable. But we note that there's probably no hope of doing exactly what we did here because, well, this was a summation, and summations behave with, adding. If I had f times g, now there might be some trick we could pull, but I don't think so. And something that we hopefully remember, and something that we hopefully suspect to be true, the integral of a product of two functions, there's not really a formula for that in terms of the product of the two separate integrals. Right? Integration by parts was kind of our attempt at figuring out a general formula, but that only works in very specific cases. So going after the integral of a product, we can't possibly do a proof like this with Riemann sums because we don't know what the hell it would equal. Now note, the Riemann sum characterization is very nice if you have an idea of what the integral should equal. If you don't, well, good thing we got those Darboux sums to fall back onto. Yeah. Which give us a characterization for integrability without actually having to know what the integral's value is. So, in that sense, if you think about it, Riemann integration is sort of the direct, I have a sequence and I know it converges to something, how do I prove it? Whereas the Darboux stuff is kind of more, well, I suspect it's convergent, but I don't know what it converges to. How about I prove it's Cauchy? Okay. Cool. All right, so our goal is the product of two Riemann integrable functions remains integrable, and like I said, we've got no hope of getting a reasonable formula for that, but we can prove that it has to be Riemann integrable, and it turns out we need 3 preliminary results to pull that off, and these are very powerful results that we will be using. So the first one is that if I have two functions and one's bigger than the other, well, then the integral behaves the way you think it should. Right, so this is also a way of saying this. So we've just proven that the Riemann integral is linear, and now this reveals the Riemann integral is monotonic. Right, because if I have a function less than another one, then the integral goes correspondingly. And now something, before we get to the proof of this, another little side talk here. Something I've noted is that this is called the Riemann integral because it turns out there's more than one way to integrate, and one of the broad ways of talking about integration is, well, right, Riemann integration is linear, we'd like integration to be linear, and another thing, integration is monotone, so you can then talk about linear functions that are monotonic, and it turns out those are called positive linear functionals. And if you've ever heard of functional analysis, then yeah. All right, anyway, let's do the proof of this, and the good news is super easy proof. All right, now note here, we're not proving an integral is equal to something, we're proving a comparison, so we're probably not going to Riemann sum this. So indeed, instead we are going to just go to partitions and some Darboux sums. All right, so take any partition. Because f of x is less than g of x, that means the integral of f, which is equal to the upper Darboux integral, is less than or equal to any of the upper sums. All right, but the supremum of f on the Kate subinterval of the partition P would have to be less than or equal to the sup of g on the Kate subinterval in the partition P, and that gives me my upper Darboux sum of g with respect to the partition P. So that means that the integral of f of x is a lower bound on the set of upper Darboux sums of g, which means that the upper Darboux integral is bigger than it, but by hypothesis we've had integration. We're integral, so we get equality. Now note, we could have proven this for upper and lower Darboux integrals, but we didn't because again, our focus is the Riemann integral, and in fact, actually, if you wanted to, you can develop a bunch of the theory of integration using the upper and lower Darboux integrals. You're not going to get everything, so you'll get some monotonicity. You will get additivity. You are going to lose scaling by whatever you want, but you will not lose scaling by positive numbers. Scaling by negatives will, flip soups into imps and stuff like that. So if you wanted to, you could more thoroughly develop the theory of lower and upper integrals and all the various properties they have. But for our purposes, we're not going to worry about that. Okay, cool. All right, so next up on the docket. So again, remember, our big goal here is to prove that the product of any two Riemann integrable functions is integral. And like I said, we actually have to kind of jump through hoops to get there. So first we need that the integral is monotonic. Next up, we need this result regarding the integral of an absolute value of a function. So if you have an integrable function, then its absolute value is integrable, and the integral of the absolute value is always greater than or equal to the absolute value of the integral. Right, and this should make some sense, because if we're thinking about this as being a limit of summations, yeah, well, yeah, then I can, by triangle inequality, bring that in. So, alright. Okay, so how are we going to prove this? Okay, well, first of all, we're going to prove integrability. Now, again, note, we're not making any claim of equality here, so we're going to get an epsilon, we'll find a partition, and then we'll get things to work the way we want it to, right? So again, remember, if you are integrable, that means we can find a partition so that the upper Darboux sum minus the lower Darboux sum is strictly less than epsilon. I claim that the upper Darboux sum of the absolute value of f on the partition P minus the lower Darboux sum of the function absolute value of f on the partition P does not exceed that same difference for just the function itself, and thus, since this is less than epsilon, that would guarantee that the absolute value of our Riemann integrable function remains Riemann integrable. Okay. All right, so we've got our partition fixed here, so I want to prove this. So how am I going to do that? Well, let's pick any two elements that live in the kth subinterval. Okay. Note that this must hold. Now, since these two elements are stuck between the supremum of the function f on the kth subinterval on the partition P and the infimum of the function f on the kth subinterval on the partition P, that means the absolute value of difference cannot exceed the difference of these two. Right, one way of thinking of that is that these two things live in the interval with this at the endpoints, so they're the furthest apart they could be is if they were at the endpoints. Now, if we look at the absolute value, the difference of the absolute values, we know that's less than or equal to the absolute value, which we then know is less than or equal to the absolute value of f of z minus f of z, so that gives me this. And now, at this point, you might be going, okay, where the hell is this going? Right, because, again, right, it's classic analysis style of just sort of, some stuff's happening right now, what's going to happen here? Well, hopefully you'll go, well, wait a minute, if I add that over, I have an upper bound for f of y. So, that means the supremum of the absolute value of f on the kth subinterval of the partition P never exceeds this for any fixed value of z. And then we pull the same trick. Bring this stuff over to the left-hand side. Now we've got a lower bound, so we get this, and then, hey, pull the old switcheroo, bring this over, and bring this over, and now we've got the supremum minus the infimum of the absolute value of the function f on the kth subinterval on the partition P does not exceed the supremum minus the infimum of the function f on the kth subinterval of the partition P. Which means that now if I look at the lower and upper Darboux sum difference, I get this inequality because, again, these are strictly positive, and I know this is less than epsilon, and there we go, we must be integrable. And finally, to get the inequality that I claimed, we know that f of x is bounded above by its absolute value and bounded baloneyed down by its negative. All right, well, that means the integral of this, which we know exists, I'm allowed to pull in the epsilon, because I can pull scalars in and out. And then I also know, oh, hey, this is less than that, which means the integral is less than it, and that's less than this. And hey, this real number is stuck between this one and its negative, and so that must be true. Bada bing, bada boom. There you go. Absolute value of any Riemann integrable function is Riemann integrable, and the absolute value of the Riemann integral does not exceed the Riemann integral of the absolute value of the function. Good stuff. Not bad stuff. All right. Cool little theorem, by the way. I like this one. It's a neat little proof. All right, so we got that in the bag. Now again, and remember our big goal, our main goal, the thing we're really after is proving that the product of any two Riemann integrable functions remains Riemann integrable. So we're doing that next, right? Almost. So it turns out that it's actually going to be, we're going to have a much better time, instead of going after products, going after linearity and then going after squaring. So we've proved linearity, we've proved monotonicity, we've proved absolute value. We will now prove that squaring does not ruin Riemann integrability. Squaring does not ruin Riemann integrability. Pretty cool. Very cool. All right. And equipped with this, we'll then prove that the product of any two Riemann integrable functions remains Riemann integrable, and we'll see there's a little trick you pull. Once you get squaring, you got it. All right, but let's get going. So we're going to prove that if you square a function, the Riemann integral, you do not lose Riemann integrability. However, we don't have any sort of formula for what the integral of a function squared is going to be. It's unfortunately not the square of the Riemann integral. All right, so let's get going. I'm out of the squeaky chair, but I'm still like knocking out the stuff. Okay, so given an epsilon, we can find a partition so that we're happy, and the so that we're happy in this case is going to require us to throw in a upper bound 2 of the upper bound of the absolute value down at the bottom here. And note, I'm using the absolute value of my Riemann integrable function and not the original function itself. And you might be going, why would I use that? Good thing we're dealing with real numbers, because when I square, I get rid of the absolute value. Alright, so here's the claim that we are going to prove. I claim, that'd be for 1 from k to I don't know why I have 0 there. It should be a 1. Oh god. I'm trying to fix it and I'm ruining everything. That's what I get. Alright, so I claim that if you look at the supremum of the function f squared on the subinterval k of the partition P, that is the same thing as the supremum of the absolute value of f on the k subinterval of the partition P quantity squared. So in other words, I can pull squaring out of this thing, but I'm going to get absolute value when I do that. All right, cool. All right, and oh look, 2 equalities claimed. Guess who's only doing 1? When you get your PhD, then you can do this. Okay, so let's prove the first equality. So we'll prove it for the supremums. You can do it for the infimums. Not much changes. Okay, so first things first, we're on the k subinterval. All right, for any x that lives in there, well, then, right, squaring the function does not exceed the supremum of it. And then what are we going to do? Well, we'll hit things with a square root. Square root is increasing, so we know that this is good. And we hopefully recall that the square root of a square gives you the absolute value, which we know is greater than or equal to 0. Okay, and note this is good for all x. So that means that the supremum of the absolute value of the function f on the subinterval k in the partition P, first of all, it needs to be bigger than 0, because all of the values are bigger than 0, and the supremum of that is less than or equal to this, because this is an upper bound for the output, for the image of the function f on the interval x sub k minus 1 to x sub k. Alright, and then now we can square both sides, and note everything is nice and positive, so squaring does not ruin anything. Alright, so we have the inequality in one direction, so now we just need to verify the other. Okay, and to get that, note that the absolute value is always less than or equal to its supremum, and note now if I square, squaring gets rid of the absolute value for me, because when you square a real number, it's positive, so the absolute value does not matter. And since I squared both sides of the equation, I now have this, and thus the function f squared, it's always less than or equal to this, so that's an upper bound for the set of outputs of that function on this subinterval, so we get this reverse inequality that we so desired. Beautiful. And there we go. All right, so we have now verified basically the only part of the proof that we really needed to verify. Specifically, right, this part right here, because now equipped with this, we're going to be able to verify that the upper Darboux sum of f squared and the lower Darboux sum of f squared gets less than epsilon, and thus we're done. Alright, so specifically now, if we look at these differences, we know that each one of these are equal to these squares, and now I have a difference of squares which factors. And, oh hey, look, upper Darboux sum minus lower Darboux sum, there's that part, and an absolute value missing, for reasons. Let me get that, oh god, where did I put it? I didn't put it in the right spot, oh no. Latex could explode, my laptop's gonna go on fire. I put it in the wrong spot again, oh no. Okay, alright. Alright, and then over here we'll have the supremum of the absolute value of the function f on the subinterval k on the partition P, and its infimum. But note, this function's bounded above by b, which means all these sups are less than b, and so are all these infimums. So I'll pick up a 2b right here, 2b or not to be. So now when I look at the upper and the difference of the upper and lower Darboux sums of the function f squared on the partition P, I pick up this stuff right here, which we now know is less than or equal to 2 times this stuff, but everything that's left over is this, and this we chose to be, this we know is less than epsilon over 2 times b. So we just get epsilon, and there we go, f squared must be Riemann integrable. Alright, and as promised, equipped with all of this, we can now prove that the product of any two Riemann integrable functions remains Riemann integrable. What is the integral equal to? I don't know, you figure it out. But here's how you figure out that a product works. By hypothesis, the sum and difference of my functions must be Riemann integrable. By the previous proposition, squaring them remains Riemann integrable. And now if I take the difference of these two and divide it by 4, that's still Riemann integrable. And note, this is equal to f times g. Multiply the 4 out, square both sides, square this all out. Here you'll pick up an f squared and a g squared, and a 2fg. Here you'll pick up an f squared minus 2f times g plus g squared, the minus sign knocking them out. And there you go. Slick trick to prove the product of two Riemann integrable functions remains Riemann integrable without having to deal with upper and lower Darboux sums of f times g, which would probably be a complete nightmare. And by probably, I mean would absolutely be. That being said, though, I actually think there is a way of doing it, because you'll have, let me pause there. The soup of the product of that stuff here is not going to work well unless things are positive. Which is why I just go to squaring. Squaring will make it positive, and then you can kind of manipulate things from there. And this little maneuver here that you see on display, let me tell you, this is a good one to have in your back pocket. So if you ever need a product to do something, this reveals you really don't actually need to directly work the product sometimes. Instead, you can figure out that squaring, adding, and scaling work instead. Because multiplication is actually just squaring, adding, and scaling. Shocking, I know. Alright. Good stuff. Good, great stuff, even. Alright, cool. Alright, so that takes care of that. So we now know that Riemann integration interacts with the 3 fundamental algebraic operations that we can perform on functions: scaling, adding, and multiplying. We also have monotonicity. We also have absolute values work. What is this? Well, what else? Right? If you look, we got some slides still. So what else? Well, time for the moment you were created for. Let me tell you. So let's now prove probably one of the most essential facts, which is that every continuous real value function is indeed Riemann integrable. So just like we learned in calculus, any continuous function can be integrated. Alright. So note, not every continuous function can be differentiated, but everyone can be integrated. So here we see integration and continuity play together very well, and there's some very deep reasons as to why this is true. Alright, so our goal now is, of course, to prove this, and what's really interesting about the proof of this is that we need this domain to be an interval AB in this proof, because we are going to use the uniform continuity, right? Oh, so if you let your mind float back, when I talked about uniform continuity, I said this is going to be very important when we get to integration, because I don't know of a way of proving this without using uniform continuity. Yeah, actually, I think that's pretty true. There's other ways of creating integrals. I think you always end up using the uniform continuity one way or the other. So, all right. Anyway, so first things first, we're continuous on a closed bounded interval, so we are bounded. Nice. Okay. So what do I need to do? Well, I don't have a way of getting formulas, right? In general, this would be if I had a formula for the integral of any continuous function, the PHEs they would be all over the place. Alright, so instead what we are going to do, of course, to verify something is Riemann integrable, is find a partition so that the upper and lower Darboux sums, the difference between the upper and lower Darboux sums gets less than epsilon. Alright, well, so epsilon's positive, and now I'm going to let eta be epsilon divided by 2 times b minus a. Now note that eta times the length of the interval is strictly less than epsilon. Sure, great. Why am I telling you this? Well, give me like 10 minutes, you'll see. Okay. Now, note that eta itself actually must also be positive, right, because it's positive divided by positive. So, since f is uniformly continuous, I can find a delta so that f of x minus f of y gets less than eta for all x and y in AB that are within delta of each other. Alright. Ooh, I have a delta. Alright, well, let's first find a natural number n, so that b minus a divided by n gets strictly less than delta. We, of course, can find such a n by the Archimedean property. And now I'm going to create the uniform partition that starts at a and ends at b, and has the length of the subintervals all be equal, specifically b minus a over n in this case, which, note, I chose to be strictly less than delta. Wasn't that clever of me? Alright, now, by the continuity, we know that on all of the subintervals, we are going to obtain a minimum and a maximum. And note something else, these points that exist, a and b, well, they have to live in this interval, which means the absolute value of their difference has to be strictly less than delta, which means this difference has to be strictly less than eta. So this is less than eta. And remember that eta was chosen very carefully, specifically so that this holds. Alright, and then now, guess what? The proof is over, because now if you look at the upper sum minus the lower sum, you get this. This difference right here we know has to always be strictly less than eta. These are all strictly positive, so the strict is carried over. Pull out the eta, here we get this, which sums up the length of the interval, and eta was chosen so that eta times b minus a is strictly less than epsilon, and there we go. Every continuous function is Riemann integrable. Yay! We did it. Alright, we are dangerously close now to the fundamental theorem of calculus. Right, we now know that every continuous function is integrable. I bet there's some antiderivatives that are going to be lurking around the corner. Alright, before we get there, though, we've got one last set of properties to talk about when it comes to the Riemann integral. And before we do that, I want to give you some food for thought. So, what did we just prove? We proved that if you are continuous, then you must be Riemann integrable. Ooh, I got a P implies Q. Do I have a Q implies P? Well, as you will prove in homework, the reverse of this, the converse of this, is not true. There are Riemann integrable functions that fail to be continuous. However, it turns out, quite surprisingly, that the converse is false, but it's really close to being true, because it turns out something you can prove, and this goes well beyond anything we have access to, something you can prove is that a function is Riemann integral if and only if it is continuous almost everywhere. And what do I mean by almost everywhere? Well, I mean that if you're Riemann integrable then our function can't be too discontinuous. So all of the points where it is discontinuous, they have to be small in some sort of sense. That starts getting into a branch of math called measure theory. So specifically, what you can prove is a Riemann integrable if and only if the set of discontinuities has measure 0, which just means that the set where it's discontinuous is like nothing, basically. So for an explicit example of something like that, the Thomé function, if you let your mind float back to that, that is in fact Riemann integrable and has a Riemann integral of 0, and note that it was discontinuous at all of the rationals. Fun. Recall, though, the Dirichlet function, though, is not integrable, and part of the reason of that is that it's discontinuous everywhere. The Thomé function, though, is continuous at all of the irrationals. It's discontinuous at all the rationals. And it turns out you can integrate it, which is pretty wild, and it integrates to 0. Yeah, good times. All right, cool. All right, so what is the last thing we need to discuss? Okay, so similar to... something that we'll do quite a bit is integrate a function not on its whole domain, but rather on subsets. Okay, so if I give you a non-degenerate interval AB, and then I split it into two non-degenerate intervals, AC, CB, I can form the restriction functions. If my original function is bounded, then so are these. So we can then create their upper and lower Darboux integrals. And for convenience, whenever we're dealing with Darboux-related stuff and restriction functions, we're just going to drop the subscript, because if we include it, it's just going to look absolutely ugly. So we're just not going to... That's interesting. Look at that. When you highlight it, it goes all the way... What the fuck? Alright. Anyway, alright, so what we're going to prove now is that for any bounded function, the lower Darboux integral splits. Meaning that if I integrate from A to B, and if I have a waypoint C, then I can split the integral in twain. Similarly for the upper ones, and oh, I'm doing it again. I'm only going to do the top one. You can do the bottom one. Yeah. Alright, so note here that we're doing this for the Darboux integrals first, because if we tried to directly attack this for the Riemann integrals, it would be a much bigger headache, so it's going to be a lot easier to do this. Okay. So let's do it. Okay, so again, as per usual, we're going to prove the first equality. All right, now this one is going to, here's the trick we're going to pull. Okay, so take a partition for the interval AC and take a partition for the interval CB. Note something about these two. If I glue these together, and specifically note that x sub n is C, and z0 is z's. Those should be y's. Why are those z's? Yeesh. Excuse me. All right. Oh wait, no, those are supposed to be z's. What am I doing? Oh my god, I'm smoking crack. Oh no, it's gonna take forever to turn. Yeah, you turn it back in the line. Okay, those are supposed to be z's. What? Oh my god. Oh god, what's going on? I'm all hopped up on a barbecue right now. I had Jeffros for lunch, so. Alright, anyway. Okay. Yeah, so note, x sub n is C and y sub naught is C. So when I stitch these together, I don't need to include y0. So note, plug in n plus 1 here, I get y1. So if I stitch these two together, I'll get a partition of the interval AB. And note this stitched together is in fact the union. Right, we overlapped a point, so we're good. And note n plus m. All right, now, if I look at the lower Darboux sum of the function f on the partition P, and the lower Darboux sum of the function f on the partition R, well, I can just glue these two together, and I'll just get the lower Darboux sum on P union R. Right, it's because the first k terms are just the things for x sub k, and then the rest are the ones for y, and that's how z was created. So you just stitch these together and you get this. And there we go. We now have the lower Darboux sum of f on the partition P plus the lower Darboux sum of f on the partition R is always less than or equal to the lower Darboux integral. And now, since P and R themselves were arbitrary, we pull our favorite move, subtract it over. This is good for all P. This is then a lower bound for, this is an upper bound for all of these lower Darboux sums. So the lower Darboux integral does not exceed that. And then we do the same thing, add this over, subtract it over, there's an upper bound, so we get this, and there we go, we get our inequality in one direction. Okay. Specifically, if you take the lower one from A to C plus the lower one from C to B, we do not exceed the lower integral from A to B. Okay. All right, so now we need to show that the reverse inequality is true, so I need to show that this does not exceed the sum, so take a partition of it. Now throw in the point C. Now it's possible that the point C already is in P, but if it's not, whatever, we can union it. So note that this creates a partition that has the element C in it, which means that I can create sub-partitions, right? So this is a partition, so it could be written as a list of elements, and the list of elements has to hit C at some point, and then continue from C and go to B. So I can split them into two partitions. I went for the Randy knockout here. Out of nowhere, the RKO gets you. All right, and now what do we have here? Well, now we pull our favorite refinement trick. R, remember, is P union C, so since this is a refinement, that means the integral gets bigger. Now, by the same trick that we pulled before, we know that the lower sum here has to be the sum of these two lower sums, and then these are less than or equal to the lower Darboux integrals, which means that this this right here, the lower Darboux integral then ends up being less than or equal to it, because this is bounded above by this, and so that means the supremum is no greater than that sum, and so we've got the inequality in both directions, and thus we've got equality. Nice. All right. And that leads us to our final result. We have now proven that the upper and lower Darboux integrals can be split in twain, and we will now verify that the Riemann integral can also be split in twain, and in particular, if you have a function that's Riemann integrable, that can only happen if splitting its domain into is individually Riemann integrable. So in other words, we are able to stitch together Riemann integrable functions. And in particular, the integrals work the way you want them to. Very cool. Very cool indeed. Oh, ow. All right. Ouchies. All right, that being said, we got something to prove, and the good news is that there's really not a lot of work that needs to go into this, because as we've just already demonstrated, upper and lower Darboux integrals behave, so the Riemann integral should behave as well. So suppose of a Riemann integrable, all right, well, the Riemann integral is equal to its lower Darboux integral, which we know splits, and we know all of those are less than their uppers, which we know we can glue back together, and we know Riemann integral, and so now we must have equality in the middle, like this. All right, now what do we do? Right, so that's, hopefully you can kind of see immediately how this would work, right? We're just sort of unraveling what I know and applying previous propositions, as you do. And we got an equality, so now with the equality, how do we approach this? Well, note that if I look at this, give a closer looky here, I could cancel that because I know this is always less than or equal to that. And note, if I combine these two together, I can delete these, and then I get the upper is less than the lower, which guarantees that the upper and lower Darboux integrals of the function restricted to CB are integrable, and so that means the restriction is integrable. And that should be, I caught a couple of goofy typos, let me fix those. my goofy typos there. Alright, it's there. Okay, so now we've proven that if you're Riemann integrable, then you're Riemann integrable on the right half of the interval if you cut it at the point C. And now to see the left-hand point, well, let's note that we now know this integral is equal to its lower one, and thus it's equal to its upper one. And note we are invoking that result from the previous, we're invoking what we already proved, which is that the sum of the uppers and the lowers go the way you want them to. All right, and here we are invoking that. We do know now that f is integrable from C to B, so the upper and lower Darboux integrals are indeed equal. That allows me to cancel and get the lower and upper Darboux integrals of f restricted to AC are equal, which means that that restriction function is integrable. And in particular, now, since we know that the integral from A to B is equal to the lower Darboux integral, which we know splits like this, we know that the integral of f from A to B is the integral from A to C plus the integral from C to B. So Riemann integrals can be split in twain, as promised. All right, now we're not done. This was an if and only if, so one last thing. Suppose that I have a function that when splitting its domain at the point C, the two restrictive functions are Riemann integrable. Then, well, the lower Riemann integral is equal to the sum of the split lower integrals, but we know this one, by hypothesis, is equal to the upper. This, by hypothesis, is equal to the upper, which we can then stitch back together. And we get the upper and lower integrals are equal, and thus I have a Riemann integrable function. And that concludes the Riemann integral properties for today. All right, so we have now set the stage. We've got all of the tools we need. The fundamental theorem is next.